This week we are going to start on a new topic. So this topic is called network models, and this presentation corresponds to the materials on your Wayne Winston's textbook on chapter 8. Let's start this by the question, why we need to learn these network models? Well, many optimization problems can best be analyzed and solved by network representations. It means that these problems can actually be solved by other approaches. Let's say you formulate them as a linear programming and then you use simplex algorithm to solve them. It is actually possible. But then you will see that these problems can be analyzed more efficiently using a network model and then a specific tool to solve that kind of network model. So the problems that we are going to look at in these chapters are shortest path problem, maximum flow problems, minimum cost network flow problems, and minimum spanning tree problems. Before we're going through these types of problems or models, we're going to look at some basic definitions that we're going to use in the network models. A network or graph is defined by nodes and arcs. So these are the two components that define a network. So in a network, we have a set of points, so all the circles that we call nodes. So we have a set of nodes and we call that set as V. So V is a set of nodes, which we can also call these nodes as vertices. So we have 4 nodes in this example here, 1, 2, 3, 4. And V is a set that contains those nodes, 1, 2, 3, 4. And then we have also a set of arcs, and then that set is called A, which contains arcs. So what is an arc? Arc is an ordered pair of vertices. Ordered means that you cannot change the order from, say, let's say 1 to 2 is different with 2 to 1 because it's an ordered pair of vertices. This arc represents a possible direction of a motion that may occur between vertices. So the arc that we have here, for example, is from 1 to 2. Remember that it has direction, so you cannot say 1 to 2 is interchangeable with 2 to 1. No, it is not, because it has a direction, so it is specific. When you say that the arc is from 1 to 2, it means the direction points going from node 1 to node 2. Okay, let's see an example. So if we define an arc j, k, it means that this arc is going from node j to node k. The starting point is always mentioned first, j, and then the destination is the second, k. So j, k means that you are going from j to k. In the previous example, the set of nodes are 1, 2, 3, 4, and the set of arcs are 1 to 2, 2 to 3, 3 to 4, 4 to 3, and 4 to 1. Now let's define these two terms, chain and path. So let's start with chain. A sequence of arcs such that every arc has exactly one vertex in common with the previous one. So this is the key here. Every arc has exactly one vertex in common with the previous arc. It's called a chain. So we have a sequence of arc, and if this happens, we have a chain. A path is a chain. So it means that we have a sequence of arcs, and then every arc has exactly one vertex in common with the previous one. But then the difference is, for path, it is more specific such that the terminal node of each arc is identical to the initial node of the next arc. So path is a chain, but then we have additional requirement, which says that not only every arc has exactly one vertex in common, but then the terminal node of each arc must be identical to the initial node of the next. Let's see what this means to make it less abstract. It's quite easy actually. So if we look at this sequence of arcs, 1 to 2, 2 to 3, 4 to 3. Let's check if this is a chain. Every arc has exactly one vertex in common with the previous one. 1 to 2 is the first, so we cannot check with the previous one, so we just take it as it is. And then this is the second arc. You see that it has exactly one vertex in common with the previous one. And then let's say the third arc. Again, it has exactly one vertex that is common with the previous arc. So this is a chain. But is this a path? Let's check. For a sequence of arcs to be a path, the terminal node of each arc must be identical to the initial node of the next. So this is the terminal node of the first arc. It is identical with the first one of the second arc. However, the terminal node of the second arc is not identical. So it's not identical to the first node of the third arc. So this first example is a chain, but it's not a path. Let's take a look at another example. So check if this is a chain. So there's one exactly common vertex, so it is okay. And then this is also exactly one common vertex between this arc and the previous one. So yes, it is a chain. Is this a path? Let's check again. The terminal of the previous one must be the same with the initial of the next one. So for the first and the second arcs, this is good. For the second and third, it is also good. So for the second example, the sequence of 1, 2, 2, 3, 3, 4 is both a chain and also a path. When we have a path, it means that we can go from the first node to the very last node in the sequence following the path. 1 to 2, 2 to 3, 3 to 4. Okay, so that's what a path means. Okay, now let's start with the first problem that can be best represented using a network model. It is called the shortest path problem. In the previous section, we see that a network is defined by two characteristics, nodes and arcs. For shortest path problem, there's one more characteristic to represent this problem. That characteristic is that each arc has a length. Okay, so in this problem, we have nodes, we have arcs, and then each arc has a length. So let's see what this problem is. So the problem is that suppose we start at a particular node. Suppose you're starting in this place. You can think of it as a city, as a location, or a place. Suppose we are starting at this node, node 1, and then we need to find the shortest path from this starting node to any other node in the network. Suppose our final destination is this location, the node 6, which is the city 1. So suppose the problem is we have to deliver something from our plant 1, to a city called city 1. The problem is that we have to find the shortest way to reach, to go from city 1 to city 6. And then the information that is given to us is that each path in this network from one location to the other location, it has a particular distance or length. So the value above of each arc defines the distance from one node to the other node. And our task is again to find the shortest path from one node to the other node in the network. So the network that you see in the previous slide actually comes from the first example. So in this example, electricity company PowerCo, it would like to send some electricity from its plant 1 to city 1. When sending those electricity power, it must pass through some relay substations. So it must pass through these other nodes. And then suppose you don't have any arc, let's say from 3 to 4, it doesn't have any arc, it means that you cannot send anything from 3 to 4. Okay, so only the arc that connects the nodes can be used to send the power. And then this value above each arc, suppose you think about it as a distance. So let's say this 3 means 3 miles apart. And then what PowerCo wants is that it wants to send power from plant 1 to 6 with the minimum possible distance. So this is really a shortest path problem. You are going to send the power from node 1 to node 6 with minimum distance. We are going to solve the problem using Dijkstra's algorithm. So Dijkstra is the name of the person who invented this algorithm. So how to start? First, we're thinking that our position currently is at node 1. So the distance from node 1 to itself is 0, right? Because we are at this node, so the distance from this node to this node is 0. And then you need to think about which node is directly reachable from our current position. So currently we are at node 1. We can reach node 2 because there's an arc going from 1 to 2. We can also reach node 3 because there's an arc going from 1 to 3. Now you write down the distance. So 4 is the distance from our current position at node 1 to node 2, which is 4. And then you write down 3 because the distance from our current position to node 3 is 3. And then what about the other nodes? Well, because there's no way we can reach nodes 4, 5, and 6 from our current position. You can see from the picture there is no arc that is going from node 1 to node 4. There's no arc going from node 1 to node 5 and node 6. So we put the infinity symbols here. The infinity here means that we cannot reach those nodes from our current position, which is node 1. Okay, so this is the very first step. And then on the very first step, we put a permanent mark, an asterisk, on the label of node 1. So these numbers 0, 4, 3, and infinity, they are called the label of the nodes. They're representing the distance, but they are called labels in this algorithm. So we put an asterisk making this label for node 1 permanent. The other labels which does not have any asterisk label, they are still temporary labels. Okay. So that's the first step. And then the next thing we're going to do is I call this step as the labeling step. So here among the labels, the temporary labels that do not have an asterisk or a star, pick one label that is the smallest. So here from the previous step, you see that we have 4, 3, infinity, infinity, and infinity. They all do not have an asterisk, so they don't have the small star on above, and then so we pick the smallest value between all these numbers, 4, 3, infinity, infinity, infinity. So 3 is the smallest, so we make this label permanent. Okay, so let me repeat. So in this else step, you check out all the labels that does not have an asterisk, or in other words, all temporary labels. Among all temporary labels, you pick one that is the smallest. Here in this case, the smallest temporary label is 3, so now we make that temporary label permanent by put this asterisk here. Okay, so that's the L step. Now, after we label a node, we need to do the update step. So what do we need to update? Well, the last time you put this asterisk, making this node label permanent, now you need to check. This is node 3. Okay, this number 3 corresponds to node 3. Now, once you are reaching node 3, you need to check which node you can reach from node 3. Okay, let me repeat. In the else step, in this else step, you put a permanent label on node 3. Now in the update step, you check which nodes can be directly reachable from node 3. We can see from the picture that node 5 is directly reachable. So now we have to update the label for node 5. How can we do that? Well, previously the label for node 5 is infinity. So we compare which is smaller between infinity, between its previous label, and the distance from this permanent label to node 5. Okay, so we are already marking this node 3 as permanent. Now you check from node 3 to node 5, the distance is 3. So you're adding, let me change the color. So you're adding this 3 with this 3. So you get this, right? So you compare between its previous label and the new label that is the result of the sum of the previously permanent label plus the distance from that node to the node that we want to update. So the result here is that the minimum between infinity and 3 plus 3 is 3 plus 3. So you update the label of node 5 from infinity to become 6. Now we are repeating the labeling step. Again, it's the same procedure. You are looking at the nodes that has not been marked as permanent. So you have 4 here, infinity, 6, and infinity. Among those numbers, pick one that is the smallest. So the smallest is 4. So now in this labeling step, you are labeling 4 as permanent. Next, you need to think again. You are labeling this value 4. This value corresponds to node 2. So now think about, if you are already at node 2, which nodes are directly reachable? Node 4 is directly reachable. Node 5 is directly reachable. It means that we need to update the value of node 4 and the value of node 5. Let's do node 4 first. So node 4 previously has the label of infinity. Now, after labeling node 2, you need to compare which is smaller between infinity or this value 4 plus the distance from node 2 to node 4. So you compare between infinity and 4 plus, sorry, actually the distance from 2 to 4 is 3. So let me repeat. To update node 4, you compare which is smaller between this infinity and the sum between this 4 plus the distance from node 2 to node 4, which is 3. So compare infinity with 4 plus 3. The smaller one is 4 plus 3, so you write down 7 here. Let's do an update for node 5. So you compare the previous label for node 5 is 6. And then after making node 2 permanent by putting this asterisk sign here, now you need to compare between this 6 and the sum between 4 and 2. Okay, so compare between 6 and 4 plus 2. Because they are the same, the minimum between 6 and 6 is still 6. So in this update step, you don't change anything. So this is the last situation that we have from the previous slide. We are finishing updating the numbers. So remember that after the updating step, we need to do the labeling step. So to do the labeling step is that we are looking at the numbers, we are looking at the labels which are not permanent yet, and pick one that is the smallest. So 7, 6, and infinity, they don't have an asterisk. So pick one, the smallest, which is 6. We make this permanent. After a node is set to be permanent, again, we need to do update step. So the 6 here corresponds to node 5. So let's see if we are at node 5, which node we can reach directly. So you see here we can directly reach node 6, means that we have to update node 6. In updating node 6, you compare its current label, infinity, compare with this value 6 here, plus the distance from node 5 to 6. So this 6 plus 2. So you compare between infinity with 6 plus 2. 6 plus 2 is smaller, so you write down 6 plus 2 or 8 in this position. After the update step, we are going back to the labeling step. You see here we have two temporary labels, which are the numbers without asterisks. You pick one that is the smallest. Between 7 and 8, 7 is smaller, so you make it permanent. So now this one permanent corresponds to node 4. Check again if we are at node 4, which nodes are directly reachable from this node. You see that we can reach node 6 directly from node 4, so we need to update node 6 again. We are doing this update by comparing its current label, 8, with this number 7 plus the distance from node 4 to node 6, 2. So compare 8 with 7 plus 2. Pick one which is the smallest. So between 8 and 7 plus 2, the smaller one is 8. So during this update step, we do not change anything. The number 8 still 8 because 8 is smaller than 7 plus 2. So by updating step here, I mean we might update the number. We might also not updating the number. But each time in the update step, you need to check which one is smaller between its current label and the sum between the label of the last node that we make permanent plus the distance from this node to the one that we are updating. Okay, it sounds a bit complicated, but it is actually very simple. You just need to do this 2 steps, one after the other, labeling, updating, labeling, updating, labeling, updating, and so on. So try to do this example on your own by hand and make sure you get the same answer. And actually, this is the very last step. So if you remember from the previous slide, the only node that has not been permanently labeled is node 6. So finally, we make node 6 permanent by putting an asterisk on here. So now you see all nodes has been labeled and our destination node 6 has also been labeled. It means that we have solved the problem. Now the very last thing is how can we read this result? So start from the destination, node 6. We are going backwards. So you check between this last node and the previous one. You check what is the difference between this node and the previous one. So the difference is 2. And then you check in this figure, is it true that the distance between 5 and 6 is 2? So you have 2 here, and you actually have 2 here. So because this distance is correct, you keep going. Now from 5 to 4. So remember, it's the difference between this 6 minus the previous one. So this is 6 minus 7. That's why we get minus 1 here. Okay, so always this node minus the previous one. Now let's check, is it true that the distance between 4 and 5 is minus 1? No, it's not, because the distance should be 2, because this is a wrong relation with the fact, so we are dropping this arrow. Drop it out. Now you try to go backwards further. It means that we're going from node 5 to node 3. Again, you try to subtract 6 with the previous node. 6 minus 3, the value is 3. And then you check, is it true that the distance from 3 to 5 is 3? That is correct. So we keep this arrow and keep going backward. Here I skip 1 step from 3 to 2 because you can see that if you compute from 3 to 2, it will be minus 1, and obviously we do not have any minus distance in the problem. So I skip that step, which actually you should do, but you may also skip it if you already see that, oh, the distance between 3 and 2 cannot be -1, so you just go further from this 3 to node 1 directly. So you need to check it, but if you're sure the distance is wrong, and then you can just skip it, like what I did here. So now we have reached the node where we are starting this problem. It means that we can read this solution like this. So it means that we're going from 1 to 3 to 5 to 6. That is the optimal solution, and then the minimum distance for that shortest path is 8. Okay, so this is how to read the solution from Dijkstra's algorithm. So the main points are you need to be able to do two things. First is running the algorithm iteration by iteration, labeling step, updating step, and then at the end you need to be able to interpret the result to say that okay, the optimal solution is going from this node to that node to that node with the minimum total distance is this. Now let's see the formal steps of the algorithm. I like to start with the example because for me, after seeing the example, it usually makes more sense to look at this formal definitions of each step in the algorithm. Okay, so first the algorithms say that we need to label the starting node with permanent label 0. So this is what we did. We are starting at node 1 and then label is 0 and then we make it permanent with an asterisk. And then it says label each node connected by a single arc to the starting node with temporary label equal to the length of the arc. So this is what we did for node 2 and node 3 because they are connected to the starting node with a single arc. Or what I said was they are directly reachable from node 1. So we put the distance 4 and 3 from our starting node, node 1. Then it says that all other nodes have label infinity. So this is what we did. And then choose node with the smallest temporary label, make it permanent. I call this L step or labeling step. So the temporary labels are, remember, the numbers here that do not have an asterisk or that little star above the number. So you see 4, 3, infinity, infinity, infinity. The smallest one is 3. And the algorithm says here, make it permanent. So this is what we did. We make the label for node 3 permanent. Remember that after the labeling step, we need to do updating step. So it is formally said like this. Suppose node I has just been given a permanent label, means that we just put an asterisk to one node. Then we need to do updating step by updating the node J's temporary label. So what is this node J? So node J is any nodes that is directly reachable from node I. Okay, so node I is the one that has just been labeled permanently. Now we need to update all nodes J that is reachable directly from node I. We have seen this procedure before. This updating step is actually comparing which is smaller, which is more minimum between the node J's current label or the sum from node I's permanent label plus the length of arc ij or the distance from I to j. Okay, we compare these two and we pick the minimum and update node j's temporary label. And then it says here continue all nodes until all nodes are labeled. It means that we need to go back to the labeling step. Check out all temporary labels again, put the permanent label on the smallest one, update again for all node j that is directly connected to node I, and then keep going until all nodes are permanently labeled by a star or an asterisk. Now finally we can do this interpretation step. We find the shortest path by working backward, finding the nodes that have labels differing exactly the length of the connecting arc. Remember, we try to move backward, and then if the distance is correct, we keep this node and keep going. But if the distance is wrong, we discard this node, and then we go back from this point and move backward further. So this is what is meant by this step. So I hope this algorithm is pretty clear for you. You need to do some practice, obviously. Let me assure you that you do not really want to be in the exam situation and you're not sure, like, wait a minute, what does it mean to label permanently? What does it mean to have a temporary label? What does it mean to do update? Please make yourself clear about all steps in this algorithm before the exam. Okay, do not try to think that, okay, maybe during the exam I can figure out. No, do everything before the exam. Make sure you understand everything clearly before the exam. If you don't understand, always you can ask me. Send your questions in the forum IDE or send me an email and I will be happy to answer all your questions until you become clear with this algorithm. Okay. Now let's go to the other example. So this example shows that the shortest path problem or model does not always have to be about a problem that you're going from one place to the other place and then find the shortest distance. Let's see here the other possibilities that we can model this problem as a shortest path problem. So it says that I just have purchased a new car for 12,000, and then the cost of maintaining a car during a year is on this table, and it depends on the age of car at the beginning of the year. So suppose you are buying a car at January 2020, it means that the age of car at the beginning of this year is 0. So this year you have to pay 2,000 for maintaining your car. Okay, and then this table shows different maintenance costs, which depends on what age is your car at the beginning of the year. And then it says that you may also trade in your car and purchase a new one. Trade in means that you sell your car and then you get some money back by selling the car that you have been used. So the trade-in price is this, and it says it depends on the age of the car at the time of trade-in. And then because the assumption here is that you always need a car, so anytime you're selling your car, you need to purchase a new car, which costs 12,000 at any time. So the problem here is that you need to minimize the total net cost, purchasing cost, maintenance cost, minus the money that you receive from trade-in, from selling your car and then buy a new one, that is incurred during the next 5 years. We are asked to formulate this problem as a shortest path problem. So remember that a network consists of nodes and arcs. Here the nodes are the beginning of the year. Beginning of year 1, year 2, up to the beginning of year 6. Why do we have the beginning of year 6? Didn't the problem say that we need to solve the problem for 5 years? Well, if you think about it, if you start at the beginning of year 1, so this is 1 year, 2 year, 3 years, 4 year, 5 years. Okay, So now it should be clear why we have 6 nodes instead of 5. You can see from the table here that you can use this car up to 5 years, because if the age of your car at the beginning of a year is 4, and then you can use it for 1 more year, it means that you can use your car for 5 years. Okay, so that's how we know where the arc can go. So from beginning from year 1, you can have an arc that goes all the way up to beginning of year 6 by looking at this table. Again, let me repeat. This table says that if you have a car which at a particular year is already has already an age of 4, you can still use it with this maintenance cost. So this is beginning of year 1, H0, beginning of year 2, H1, beginning of year 3, H3, sorry, beginning, I'm sorry, I'm quite confused with that. It can be quite confusing, right, between year and age. At the beginning of year 1, my age is 0, my car's age, I mean. At the beginning of year 2, my car's age is 1. At the beginning of year 3, my car's age is 2. At the beginning of year 4, my car's age is 3. At the beginning of year 5, my car's age is 4. And then you can use it 1 more year so you can reach the beginning of year 6. So that's why you have an arc that goes from 1 to 6. Of course, if you can use it all the way from 1 to 6, it means that you can also have the arc from 1 to 5, 1 to 4, 1 to 3, 1 to 2. And then from 2, you can also have 2 to 6, 2 to 5, 2 to 4, 2 to 3, and so on. Okay, so that's how you're getting the arcs. Next, I'm going to talk about how we can get the value here above each arc, how we can get this distance between nodes. Or actually in this problem, those values corresponds to cost. But in the shortest path problem, the value above an arc is a distance. Let's start with the simplest one. You are buying a new car at the beginning of year 1, and then you are planning to use it just for a year. So at the beginning of year 2, you will trade in your car and then get a new one. Okay, let's see how much that kind of plan costs. So buying a new car at the beginning of year 1 costs you 12,000. And then at the beginning of year 1, the age of your car is 0. So the maintenance cost for this year is 2,000. So for this year from 1 to 2, the cost is 2,000. But then in this plan, it says that you are just planning to use the car for 1 year. It means that at the end of the first year, you are selling the car. At the end of the first year, your car's age is already 1, right? Because you bought the car at the beginning of this year. So at the end of this year, like 31st of December, the age of your car is already 1. For the car that has an age of 1 year, you can trade it in with, you get the money of 7,000. Right? Why is this the case? Because this is the cost, this is the cost, but then this is something that you get from selling your car. So the sign is here, the cost is plus, plus, but this is something you get, so the sign is minus. Okay. Why is this the case? Because the problem asks you to minimize the cost. Okay, so 12 plus 2 minus 7 becomes 7. So that's the number that you see here. Now you may ask that, wait a minute, didn't I say that after you trade in a car, you need to buy a new one? Yes, but that would be the problem for Note 2, right? So if you are in Note 2, it means that you need to start with buying a new car, and then maintenance from 2 to 3 is 2,000, and then at the end of the second year, you trade in your car, and then you get 7,000 back. So again, this is 7. So what I was trying to say is that this arrow means that at this node, you are buying a new car, and then you use it until the end of this arrow, and then you sell your car for trade-in. But the problem of buying a new car to use will start at the node. So at the end of an arrow, what you're doing is simply just sell the car for trade-in, and then you get the money from that trade-in. That's all. On January 1st of the next year, then you need to buy a new car. Okay, so I hope I make it clear that this arc means that you just up to the end of a year, you sell your car, and that's it. At the beginning of next year, you buy a new one. Now you might also ask, like, why from 1 to 2 the cost is 7? From 2 to 3 the cost is also 7. Well, think about it. It doesn't matter at which point of time, as long as you are following the same plan. Buy a new car at the beginning, use it for a year, and then at the end you sell it for a trade-in. The total cost will be the same, regardless of what time you are doing that. Okay, so that's why here the cost is always the same. 7, 7, and 7. So from 1 to 2 it's 7, 2 to 3 is also 7, 3 to 4, 4 to 5, 4 to 6, they're all 7. Okay, so that's the explanation. Now let's try to check the other extreme. If I use my car, so I buy a new car at the beginning of year 1, and then I use it all the way until the end of year 5 or the beginning of year 6. Let's check if the cost is 44. So at the beginning of year 1, I bought a new car. So it cost me $12,000. And then I have the maintenance cost of 2,000. This is from year 1 to year 2. Year 1 to year 2. And then because I keep using this car, I have another maintenance cost of 4,000 I mean. So $4,000 is from year 2 to year 3. And then I keep using this car, so the next year I get I need to pay $5,000 for maintenance. So that is 5,000, and then let me write it down. This is 2, this is 4, this is 5. And then I keep using this car, so I need to pay 9,000 here for the maintenance. And then for the final year that I'm using my car, I need to pay 12,000. Now at the end of my 5th year, I sell my car for the trade-in. So the age of my car is already 5 years because I keep using it for 5 years. 1, 2, 3, 4, 5, right? So at the end of the 5th year, my car has already had no value at all. So the trade-in price for my car is 0. So I got nothing from selling my car. So that is minus. So the total cost is 12 plus 2 plus 4, this is a plus plus 5 plus 9 plus 12 minus 0, and that is equal to 44. So that's how you get these numbers. You can check on the textbook on how to get the other numbers, or you can also practice on your own to make sure that you get this computation. It's quite simple. You just need to be very careful in thinking about you buy a car at the beginning of a year, you use it for that year, and then you sell your car for trade-in at the end of a particular year. You start buying a new car at the beginning of the next year or the next node. So that's the end of this presentation about shortest path problem and then how to use the Dijkstra's algorithm to solve that problem. In the next presentation, we're going to look at a different type of problem which can also be modeled by a network model. It's called maximum flow problems. So this is the end of this presentation. As usual, if you have any questions, confusion, or anything, please feel free to ask me questions through IDE or send me an email or write a comment. Thank you.